So Wenjing, can you, yeah, we can see your presentation now. So.
Yeah, thank you very much, so Alberto, and for your introduction and also the invitation to this seminar. I'm happy to have the chance to present the result on the molten halide salt electrolyte in low temperature sodium-based liquid metal batteries. I have to see all the other presentations in this seminar. So most are about the dynamic simulations, but this time I will give you some more so things about the electrolytes, because our group has many years experience in molten salt for thermal energy storage in renewable energies. So in my presentation, I will at first to introduce so our institution, and also have a introduction on the background for the large scale energy storage. And after that, I will show you some results on the development of the molten halide salt for the thermal energy storage, mainly on the corrosion control. Because I think maybe such a knowledge is also important for the liquid metal battery development, because liquid metal battery is used at high temperature, and if it want to use for the commercial application, so for more than 20 years, I think the corrosion is also a very important the things. So I hope such a knowledge can help for the liquid metal battery development. And after that, my focus will on this liquid metal battery. Yeah. So yeah. Okay. So as so Obet has introduced, so my institution is German Aerospace Center, DOR, and our institution has so three functions. First is as the national research institution. It has 6 research areas. Energy is one of the most important areas. Our group is working in this area, and the DOR has other functions as national space agency, and also the National Projects Management Agency. The DOR has more about 9,000 employees, and with 40 institutes and facilities at 20 sites in Germany, and also we have some international offices in other countries. And also in Spain, we have a research site for the concentrated solar power the technologies. That is really related to our research, because the molten salt electrolyte, the storage technology has been used in CSP technologies. And our institute has about 200 staffs and have 5 locations. I'm working in the main location in Stuttgart. And so DOR has so this research, energy research topics. So our institute so focus on the CSP technologies, and also the energy storage technologies, the thermal, chemical, and electrical storage technologies, and also fuel cells, and also the energy storage analysis and technologies assessment. And here you can see the 2 pictures. This is one. This is a molten salt the text facilities. So of our group, I think it is the largest one in the world. It can do the experiment using the 100 tons the molten salt. And here, this picture shows the synthesized light at DOR. It's also the largest in the world for the synthesize the sunlight. It can be used for the CSP, so technology development for every day and every time. So our research group is for the heat storage in molten salts. We do the research from materials level and to the components and to the system levels, and from milligram to tons level. So as shown here, so we do the experiment. So our target is to push the commercial application of the current molten salt electrolyte, molten salt so technologies, and also to develop new molten salt electrolytes for new applications. So maybe as you know, so in Germany, so we have a very important national program for the energy transitions, and in the new energy systems in the future, it will be more and more not stable power from the photovoltaic and wind energy, and so until the 2038, all the coal power plants in Germany will be shut down. That means after that, no coal power plants will be used. And also next year, the last nuclear power plants in Germany will be also shut down. So that means in the future, there will be a significant increase of the not stable power from the renewable energies. And that's why we want to develop the largest scale energy storage to stabilize the grid. So now, so in the world, the global capacity for the grid, the connected storage, the most one is using the pumped hydro technologies. It's more than 90%, but the rest, the main the technologies are semi-energy storage and also the batteries technology. So the molten salt semi-energy storage technology has been used in the CSP, and in 2015 it has already more than 30 gigawatts hour. And I know that now it's already more than the 200 gigawatt hour the capacity. And so for the CSP and for the energy semi-energy storage, we are developing a new molten halide salt for the high temperature heat storage. So the main work is on the corrosion control. So here is the state of the art CSP power plant. So it uses the molten the nitrate salt. The operating temperature is between 200 to 550 degrees C. And so compared to other storage technologies, the molten salt heat storage is inexpensive, and it is not toxic and not flammable. It's safe, yeah, and it uses the larger scale, so unpressurized tanks. And besides the CSP, so molten salt energy heat storage technology has other potential application to the grid, the connected storage. So in our institute, we are developing so power to heat and heat to power again. This such electricity storage technologies. We name it the Na-K-LUM battery, and that means the storage based on the heat storage technology. And compared to other technologies, it has very larger storage capacities. It can be gigawatt hour scale, and also the energy efficiency is it can be also higher than 40 to to and then up to the 70%. And if we using also the heat, so the overall energy efficiency can more than the 85%. As shown here, so such a technology can be used to transform the coal power plants to renewable the power plants. So now, as we know that all the heat for the power plants is come from the coal, and in the future we can use more and more thermal energy storage and to reduce and to increase the coal power plants flexibility. That is the first step, and the second step is to also use some electricity from the renewable energies, and the final target is to get the canoe battery. Yeah? So that means that we will not use the coal; we just use the renewable energy and stone in the molten salt, and using the heat in the molten salt can give the flexible power. So also for our work, so we are developing the next generation molten salt heat storage technologies. So it will be used at even higher temperatures, for example, up to 800 degrees C. Then it can increase the performance, the storage performance, and the other the performance. So such as new molten salt heat storage technologies can also be used for next generation CSP technologies. And in such a CSP, you can see here, so get the heat from the sun and store the heat in the molten salt at high temperature, so above 700 degrees C. Then using the heat to generate the electricity, and the supercritical CO2 power cycles can be used for a high energy conversion and for low the energy cost. So, but for the high temperature, so next generation molten salt and the heat storage technology, we have to choose a right salt, as shown in this diagram. So now we use nitrate, yeah, but we want to increase the temperature. We needed more similarly stable salt like the chloride or the carbonate. But compared to the chloride, the carbonate has to use the lithium carbonate, and then to have a low melting temperature, but it will lead to very high material costs. So now we focus on the chloride the system. So the chloride has the lowest the salt cost, but if we cannot control, but it's very corrosive. If we cannot control its corrosivity to the metal structure materials, so the material of the tank will be very expensive. Then, as shown here, the cost for the tanks will be very higher. So if we want in the future, we want to use the molten chloride salt technology, we have to control its corrosivity. So then we can use the cheaper alloys as the structure materials. So in our group, we have do this systematic research on the molten chloride salt for the heat energy storage. The first, we selected the promising chloride salt mixtures, and then we study its the corrosion mechanisms, and also we develop the corrosive impurities and monitor technologies based on the electrochemical method, and also use the electrochemical method to purify the salt to reduce its corrosivity, and also by adding some corrosion inhibitor to reduce the corrosivity of the salt, and also with some compression and to develop the new structural materials. But during to the time, so here I just introduce so these two topics because they maybe have some knowledge for the liquid metal battery development, and so it can help to control the liquid metal batteries, so sort of corrosivity. So first is the corrosion mechanism of the conventional so iron, chromium, and nickel alloy. So we do the immersion test at 700 degrees C and 500 hours, and so the atmosphere is argon. So in the atmosphere as the liquid metal battery, and also for the semi-energy storage application, and use this the salt mixtures and put the alloy samples inside and heat it up to high temperature, and after 500 hours and take it out to do the analysis. So the corrosion measurement to find out the expensive nickel-based alloy has the best corrosion resistance, but so even yet, so its corrosion rate is higher than 500 micrometer per year, but for 200 hours, usually the corrosion rate should be below the 50 micrometer per year. So from the SEM and EDX analysis of the closed section of the samples, we find out the corrosion mechanisms. The conventional alloys. So first, it's the chromium element is dissolved. And also important, the mechanism is that the corrosion is driven by the impurities like the magnesium hydroxide ion in the salt. I think this is also possible for the molten salt electrolytes for the liquid metal batteries. Sometimes so it contains some very strongly hygroscopic salt like aluminum chloride or magnesium chloride. So it will be also absorb some water inside, and when it heat up to the operating temperature of the battery, so it also will the impurity, corrosive impurity will be produced. So my suggestion is so should to pay attention to the corrosion of the salt in the batteries, and so we proposed the corrosion mechanism is that so the main impurities come from the atmosphere or from the adsorbed or the hydrolyte, the water in the salt, and during the heating, the magnesium hydroxide ion will be produced, and it is stable in the molten salt and can dissolve in the molten salt. Then it can corrode the alloys at high temperatures. So regarding this corrosion mechanisms, we have developed some corrosion mitigation method, for example, by adding the magnesium corrosion inhibitors. So we also do the similar corrosion test, but in the molten salt, we put some the magnesium metal inside. So after comparison, so with the magnesium or without the magnesium, we find out with magnesium, the corrosion rate of the conventional alloys will be significantly reduced to about the 10% compared to the case without magnesium addition. And the inhibitor mechanism is, we think by ending the magnesium, the redox potential of the molten chloride salt will be reduced, and to reduce to below the chromium corrosion level. So now I go to the sodium-based liquid metal battery. Our result. So liquid metal battery is a very promising great scale storage because its storage cost is low. If we can find out using the low cost metals and low cost molten salt electrolyte, and it has very longer life for more more than tens of thousands of cycles and easy to scale up because it has all liquid interfaces. The battery will be can be used for long time. And the state of the art, the battery, so our Chinese partner has published several years ago. So the result, as shown here, it's the lithium, the best liquid metal battery. It shows very promising performance. For example, so it has very low self-discharge rate, and its efficiency is very high. And the recycling and the loss is very low, and the cost is low. But the problem is that if we're using the lithium in the future, maybe the price, the battery, the cost cannot be well controlled. So and here is a comparison of the state of the art liquid metal batteries. So yeah, the lithium liquid metal battery has been introduced, and it has excellent performance in level scale, and the Ka-LUM, the best the best lithium liquid metal battery, it with excellent performance. So it has been achieved in conventional scalars. Yeah, I heard. So now they have a project to use this liquid metal battery for 500 megawatt hours storage. And but the sodium-based liquid metal battery still, so it has without the excellent performance, even in large scale. So and so we think and some reviews says maybe the molten salt electrolyte is the key challenges because it needs low to be have low melting temperature and also good the electrochemical properties. And as shown here, so this two, it has good battery performance, but the sodium liquid metal battery, because they use the sodium salt mixtures, and the melting temperature cannot below the 500 degrees C, and the working the temperature is about the 600 degrees C. So at so high temperatures, the sodium metal solubility will has the problem. Then the self-discharge rate will be higher, and also at high temperatures, so many problems like the corrosion. So if usually, so from our heat storage experience, we think if the temperature is higher than 550 degrees C, so we need to use expensive alloys. So we in our project with our partner in China and in Germany, China is the Huazhong University of Science and Technology and the KIT. So we wanted to develop a low temperature sodium-based liquid metal battery. So using sodium, it can reduce the battery cost, and low operating temperature can reduce the cost of the structural materials. And also we hope this new liquid metal battery has the similar excellent performance as the conventional batteries and also the lithium-based batteries. So molten halide salt are promising electrolytes for such a battery, and because it has high electrochemical stability and has the highest thermal stability, and also highest conductivity, but low the cost. So, but it has problem is usually the halide the salt has the highest melting temperatures. for the especially for the sodium-based liquid battery. So we have developed a method to selection and optimization of the molten salt electrolyte for the liquid metal batteries. That has 5 steps. First is using the phase D1 simulation regarding this melting temperature to scanning the salt mixtures. Then after that, use the measurement the method to measure the melting temperature. And after that, to use the experiment or the simulation to determine the key salt properties as the electrolytes. And after that, do the cost analysis of the materials. And after that, using the battery to test the selected molten salt electrolytes. So maybe it can also do some several recycles to get to the optimal and the salt mixtures as electrolytes, and also the optimal batteries performance. So regarding this potential, so the salt mixture should containing the online the cations like the lithium, cation, and barium and cation ions, because so they should be more negative than the sodium metal, yeah, to have the chemicals compatibility with the sodium metal. And also we use the Fexager simulation, the thermodynamic modeling, to reviewing this and also reviewing the literature. We find out the 2 groups of low temperature, low melting temperature, and the salt mixtures for the sodium-based liquid metal batteries. One is containing the lithium ion, so it's lithium, sodium, and potassium, so Halide salt mixtures. And another is without the lithium. Regarding this lithium chloride, maybe it's expensive, so that is this system. So first we study on this lithium containing the salt system during to its low melting temperature. Yeah, it can be low than 300 degrees C. So we use the thermodynamic modeling on the first on the ideal salt mixtures. We can see here. So it's a salt mixture can be let's say it's performs as a petrol so binary salt. That means the eutectic lithium and potassium the salt mixtures can dissolve the sodium the ideal salt, but its maximum solubility is about 12 more %. If above 12 more %, then the melting temperature will increase very fast. And so from the experience of the battery test, we hope the sodium ion concentration is higher for higher and so ionic conductivity, but we need to have the low melting temperatures. So we started this so 6 salt compositions from 0 to 12 more %. Then also we have started this chloride the salt systems. So compared to the IDIT, it has a little bit higher melting temperatures, about 60 degrees higher, and the performance the properties are similar as the IDIT. It also it's like this, and the sodium chloride is dissolved in the eutectic lithium and potassium chloride, the eutectic salt mixtures, and its solubility is about 10 more % from the simulation. But as compared to IDIT salt, so it has higher thermal and electrochemical stability and lower the cost. So after that, after the simulation, we use the DSC and altimeter as a method to determine and the measure the melting temperatures. So the measurement find out the solubility of sodium iodide is about the 6 to 9 more percent. It's lower than the simulated values, and if it contains 12 more percent. So in the DSC we can find out the second the white piece, and that means some solid salt inside. It's not, it cannot be used for the liquid metabolically if the operating temperature is this range. So and another, we do the determination of the key salt properties as the electrolytes. For example, the sodium and the solubilities and also the conductivities. So the solubility from the simulation, we already consider the dissolution reaction. So according to the literature, and we find out if below the 550 degrees C, its solubility is quite low. And so and the estimated self-discharge rate is also low enough. And but its value can be so under the estimated because due to other dissolution reactions maybe. And the experiment has been done. I will show you later. And the sodium ion conductivity. So based on the literature data, we find out it's about 28 millisiemens per centimeter for the temperature higher than 350 degrees C. So if regarding to compared to other so electrolyte in the conventional batteries, it's high enough. So also we do the determination for the chloride salt, and it's also has very low solubility of sodium metal, and it's estimated self-discharge rate also low enough. But it also has a similar problem. So we needed to do the experiment. So also the sodium ions conductivity is estimated, and it's high enough. So and here's a comparison with other electrolytes. So here it shows the setup and the analysis method to measure the sodium solubility. Here we use the glass carbon crucible to contain the salt, and using a stainless steel to contain the sodium metal. And we heat it to high temperature, and which is the sodium so dissolved in the salt. So we do several measurement, and usually after 1 hour the solubility is already the highest. So we do the titration measurement. So we put the salt and dissolved in the water, and it will has such the reactions. The sodium hydroxide will be produced, and use the HCl to do the titration. Then from the titration value, we can know the sodium metal solubility. So from the sodium solubility, we can use this simple model to calculate the self-discharge rate using this equipment. So from the concentration gradient, we can calculate this self-discharge rate, and we use the value from the literature here. And our titration result shows that as shown here, when the in the salt the solubility of sodium chloride increases, that means the more sodium chloride inside in this temperature range, we find out the sodium solubility is decreases. So but they are low, so less than 0.1 or more percent. So that means the literature said this theory of dissolved reaction maybe not correct, yeah, or not completely correct. We needed to do more study, but the result, the experimental result, confirms that the sodium solubility is low. Yeah, it's larger than the simulated values, but it's low, and the estimated and the self-discharge rate is below the 0.4 milliampere per centimeter quadrat square. Yeah, and then we can have such conclusions. So for the selected the molten salt electrolyte, the sodium solubility is low enough for acceptable self-discharge rate. So we can use this molten salt electrolyte for the battery test. So we also do the cost analysis. So compared to the chloride, the added is salt mixture is expensive, and when it contains the lithium, yeah, the temperature, the salt mixture is more expensive than the published the salt mixture. But so in the liquid metal battery, usually we use very thin salt, very less so molten salt electrolyte to have low resistance. So after the cost analysis, we think the effect on the battery cost is small. And also we have considered this salt the corrosivity against the structural materials, yeah, the metals or like the alloys. We find out because the sodium metal, when it has a contact with the salt, it has a similar function as the magnesium metal. It can reduce the redox the potential of the salt and reduce the salt the corrosivity of the salt. So we think it's not a critical issue because the liquid metal battery is operated under inert to the atmosphere, and also it has the inhibitor effect of the sodium metal. So if regarding the salt corrosivity, the conventional stainless steels can be used. And we are also do the corrosion test at the 500 degrees C, and it also shows it has no problem. But maybe the problem is the corrosivity of the heavy metal, so cathode and also the sodium vapor. Yeah, so we need more study in this area to have to ensure the battery's safety. So we do so our partners host in China to do the battery test using the selected molten salt electrolyte. So at first we use the sodium the chloride salt mixtures, and working the temperature is 400 to 450 degrees C, and more than 300 discharge and charge cycles, and so test and the current up to 1000 milliampere per centimeter square. And our main result is that, so now this using the optimized salt mixtures, the sodium, the liquid metal battery can be used for low temperature. So much lower than the conventional and the state of the art, the liquid metal battery. And this efficiency, so for example, here the efficiency is higher than 96, and the energy efficiency is higher than 80. Yeah, it's similar as the conventional batteries. And the estimated self-discharge rate from the sodium solubility is also low, and the battery test also shows that the self-discharge has no problem. And one amazing result is that, so after 300 cycles, we cannot find almost no the capacity of bending. So here is the summary and outlook. So our research group has the knowledge on the molten salt chloride for the TES, and we, for example, the corrosion and the salt purifications. Such knowledge can be used for develop of the molten halide salt electrolyte for the sodium-based liquid metal batteries and also other liquid metal batteries. So the molten halide salt as electrolytes in liquid metal battery. So we have developed a method for the selection and optimization of the salt mixtures, and it has been tested and been published. And so the lithium, potassium, and the sodium the halide salt mixtures are found to be promising the electrolytes for the sodium liquid metal batteries. And the sodium liquid metal batteries with the optimized the salt, molten salt, the electrolyte shows very promising the good the battery performance. It has the similar battery performance as the conventional batteries, the calcium based the liquid metal batteries. And also, yeah, maybe you also know, so Na-based has also shown that, so we have a cooperation project, it's ongoing. It's a EU project, yeah, its name is SOSTIC, and we also involved in this project. And our main task is also develop of the molten salt electrolytes for the sodium zinc batteries. I hope so. Yeah, after 1 year or more, so we can also give show the result from this project. So thank you very much. That's my presentation, and you are welcome to give me questions.
Great, excellent. Thank you very much for a very nice presentation. And as you just said, we are open to any questions from the audience. So please. We are open to any question to the speaker. Also, feel free to write on the chat if you want. Professor Ramos is asking on the chat about, is it possible to reduce the corrosion by applying a coating on the internal surface of the containers for the case of thermal energy storage system or for the liquid metal batteries containers?
Yeah, so we also to test the coatings on the structural materials of the alloys. Mm-hmm. So I think yes, so it's also can be used for the liquid metal batteries, but we should so pay attention to the chemical the compatibility mm-hmm. with the salt and also the electrode. So we should do at first do the chemical compatibility test and to find out the coatings can stable when it contact with the electrolytes and the salt. For example, the alumina chloride, we find out it's no problem for the salt and also the sodium metal, but we have no idea for the heavy metal. And the second is that when we have this alumina coatings, so it's we should pay attention to its long time or the long time stability. So for the heat storage, we have the problem because the molten salt will be changed its temperature, and that means the coating will have the same as soccer. The temperature change very faster. Then such as ceramic coating may be broken and have some cracks. It's very dangerous for also for the corrosion or for other safety. Yeah? So such as a test also should be done. But I think yes, yeah, for the batteries, it can be a promising method to control the corrosion.
I see. Thank you. Michel Rivero is asking, is there any effect of the impurities in the molten salts due to corrosion on its physical properties? He said that as far as he understands, these impurities might trigger nucleation.
Sorry, can you repeat your question again?
Yeah, is there any effect of the impurities in the molten salts due to corrosion on its physical properties? So how the impurities affect the physical properties?
The question is about so how is the impurities affect the properties, yeah?
Right.
So the same properties or the electrochemical properties. So yeah, if regarding the same properties, the impurity inside, the, for example, the magnesium hydroxide impurities inside, we usually it's at the ppm level. So very low, so 1,000 to the ppm. Usually when the impurity level is higher than the 100 ppm, so at in our case, so it will be very corrosive. So we should control to very low concentration, and at such low concentration level, it has not a very significant effect on the similar properties. But I'm not sure, so it can be has effect on the electrochemical properties or not. For example, for the sodium-based liquid metal battery, in the molten salt, it will be contain some oxide. So, for example, sodium oxide. So it can be changes this changes this electrochemical properties. But we have no the experiment. So just that's why it's important if we use the molten salt electrolyte. Before that, we should do the salt purification, and to have a standard. Yeah. So for the liquid metal battery, for the commercial applications, is how is the standard for the molten salt electrolyte? The impurity and the level should be below which level. So I think it's also a very interesting topic for the future if we want to use the liquid metal battery for large scale applications.
Mm-hmm. Yes, thank you. Any more questions from the audience? By using sodium, either in the, well, for the liquid metal batteries, is it possible to have electrolysis at some point? I don't know, to the presence of some impurities or chloride. What do you think?
So you ask the sodium-based liquid metal battery, yeah?
Yes. Exactly.
So you ask the impurity in salt?
Yes, it's impurity in salts, but will it probably induce electrolysis inside the battery, or it is not possible? I mean, maybe to the presence of some water or oxygen or something. That is it possible to have the presence of an electrolysis process inside the battery or not?
I'm not understanding completely your question. So yeah, to my understanding, so the battery should be closed, yeah.
Right.
So in the atmosphere and no oxygen and water inside inside. So water and oxygen come from maybe from the molten salt electrolyte.
Sure.
Yeah. Before that, you put this in the battery and close it and heat it up. So if it has the sodium metal together, so as I have shown that, so the hydrolysis reaction will take place. The water will be to the hydroxide ion and oxide ion in the molten salt. Yes. And this hydroxide can react with the sodium metal. The sodium metal can to be the sodium oxide. Then in the molten salt electrolyte, I think in the stable conditions, all these oxide will be so stay in the molten salt electrolyte. And in the gas atmosphere, I think it will be some so hydrogen inside. The hydrogen produced, yeah. So it's also yeah, so it's dangerous, or so it's not good. So that's why I also should already said, so before use the molten salt electrolyte, should do the salt purification. They use the method as I have introduced. For example, put the sodium metal in the molten salt in the salt and heat it up, and take the salt out and use for the battery. Or using the electrochemical method, for example, using the electrolyte and give the voltage, and the hydrogen can also be produced, and the impurity can be removed. So we have done so, yeah, in our molten chloride for the heat storage. So
thank you. Okay, so any more questions from the audience? Maybe I will look at the chat. How different are the expansion coefficient values for these different molten salts? In terms of, I don't know, of a shooting of the system, you know, everything will solidify, and then it will necessary to heat up again. So will it cause any crack maybe, or it is not possible because of the thermal expansion coefficients of the molten salts? How different are they?
So the question is on the so self-discharge rate, yeah?
Okay, yes, basically.
Yeah.
Yeah.
So yeah, this model is very simple. Because I study the chemical engineering, and we also do many such as simulation. So in the chemical industries, yeah. So I think the self-discharge using this equipment can get a very lovely value, yeah. So how is the self-discharge rate? But of course, we want to know the exact value. We should do the experiment, yeah. But here, for to calculate the self-discharge rate, so for different salt mixtures, I think the diffusion coefficient is not the same. But usually for the molten chloride salt, so like the sodium or potassium or magnesium, their value is similar in this value. And also I remember there is a diagram to estimate the diffusion coefficients when the calcium is different. Usually the calcium is larger, then the diffusion coefficient is low. But it is in the range, yeah. So the 10, so -4 or -5. So not very larger change. So from here we can get to the safety charge ratio, and to give some suggestions. For example, when we select this the salt electrolyte, we should know the so for example the sodium solubility, the maxima or the maximum the level we can see. Yeah. For example, so it cannot higher than 1 mole percent the solubility, and then it can help us to determine the operating the temperature of the liquid metal battery. Yeah. But also, yeah, of course. So if we want to know this more or have more knowledge, we need more study to set up, for example, a test cell, and it has the concentration gradient and defined, then measure it. So how changes this the concentrations of this, then using the simulation value, we can know this the self-discharge rate.
Thank you. Yes. Are there any questions? Is there any questions from the audience? Maybe. Also, feel free to write in the chat.
Yeah.
Okay.
So
Yeah. It seems that there are no more questions. Would you like to add something, maybe, Wenjing? Yeah.
Yeah. If you have question, can direct so using the audio and to ask me.
Yeah. Perfect. So it seems that there are no more questions. So feel free to email Dr. Wenjing Ding in case of more questions or any doubts about the presentation, right? You are open to any questions after the presentation. Okay, no questions.
Okay.
Thanks for the important. Yeah. Well,
Thank
yeah.
you also very much, yeah, for the organization.
No, it is my pleasure. Thank you very much for accepting the invitation from Norbert and from me, and we wish you all the best, and hopefully we could meet all together in person soon. Thanks again for the very nice presentation, and let's keep in touch.
Okay, so you're welcome, yeah? Okay.
Yeah.
So today is it's over, yeah?
Yeah.
Okay, bye-bye.
Bye-bye. Thank you very much again.
Bye-bye.
Yeah, thank you very much for everyone.
Bye-bye.
In this meeting.
Alberto, bye-bye.
Bye. Hopefully
Thank you. Thank you, Alberto.
Yeah.
Thank you, Wenjing.
Thank you. Bye-bye.
Bye-bye.
Have a nice day, everyone.
Have a nice day.
Nice weekend. Thank you, Norbert. Thank you, Stephen. Bye. Jose.